all of you. Myself, M.D. Sajjad Ahmad, working as an assistant professor in Katihar Engineering College, Katihar. It is my honor to introduce Dr. Vikrant Bhateja, sir. Dr. Vikrant Bhateja, sir, is an associate professor in the Department of Electronics and Communication Engineering and also the Dean Academic in Sri Ram Swaroop Memorial Group of Professional Colleges, Lucknow, UP. He is doctorate in ECE, a specialization in biomedical imaging with a total academic teaching experience of 18 years. Sir has 165 publications in reputed journal, international conferences, and online book chapter contribution, out of which 30 papers are published in SCI indexed High Impact Factor Journal. He is editor-in-chief of IGI, Global International Journal of Nature Computing and Research, and ACM and VDL indexed journal since 2017. He is received the certificate of outstanding reviewer for the years 2016 and 17 respectively in prestigious Elsevier journal like AEUE, Measurement and Computer Method and Program in Biomedicine. He is senior member of IEEE with H index 31, and his publication has total impact factor of nearly about 75. Now, I would like to invite Dr. Vikrant Bhateja, sir. Please enlighten us with your session.
Namaskar, everyone. First of all, I'm very thankful to Katihar Engineering College, Ranjana Madam, Honorable Principal Madam, Dr. Ram Kumar, for giving me this platform to share my learning, my knowledge with you all, my colleagues. And this is an added pleasure that I've been associated with this FDP second time this year again, because last year also I was a part of this similar FDP on medical imaging and machine learning. And this time this FDP has grown to a 5-day ATAL FDP program. Further, I would also appreciate, the organizing team, the way it has been planned, the way the entire FDP has been structured, because I can see that planning the FDP for medical imaging, the organizers have tend to plan and cover different types of imaging modalities like CT scan images, X-ray images, MRI images, and also their prospective applications in terms of machine learning, deep learning, and signal processing. So just sharing my slides. I hope the slides are visible. My screen is visible. Okay. So the topic for today's discussion in this FDP is non-linear filters for enhancement of mammograms. Now, non-linear filters is a very vast domain if we understand from point of view of signal processing. And another, if we talk about enhancement, so sometimes we feel in this manner, or we perceive it in this manner, that enhancement is just limited to one function that we are using from our toolboxes in MATLAB or Python or other digital libraries. But with the discussion, you'll certainly come to know that how these two different things like nonlinear filters, their deployability for image enhancement, and that to a very specific category of images, that is the breast X-ray images, mammograms, has turned into a very vast domain of research. So my entire discussion will be so planned that it will be delivered in the form of a research case study on breast cancer detection. So about the session, taking an overview, a quick overview of this session. I'll be introducing the session with computer-aided analysis of mammograms. Then we will move to linear versus non-linear filters. Later on, we'll come to the mathematical modeling of non-linear filters. We will have a detailed discussion of Volterra filters. Then we'll talk about non-linear filters, their associated challenges and research gaps. Then the major filter, which is my contribution, that is non-linear polynomial filters. Then we'll talk about image quality assessment of mammograms. Lastly, we will take up the simulations, the result part, and again, we will close the discussion with very important thing, that is the directions for new research problem formulations, because I know that there will be many colleagues who would be purposely doing this program just to look for some topic in the form of their to start their research in the form of their MTech research or their PhD research. So this will be the most fruitful discussion for them, where I'll be certainly giving directions that how this particular research could be further extended to develop new research problems. Well, friends, I would just apologize in the beginning that I have been down with viral from last 2 days. So, my voice is a little affected with that. So, apologies and kindly bear with it. Now, if you talk about the content resource, then when I started research on this particular topic, my immediate reference in this was just 2 conference papers which were published in 2009 and 2010. And after that, when I started working in this domain, the very initiating work which I published as a novel contribution in prestigious IEEE Census Journal was this a robust polynomial filtering framework for mammographic image enhancement. Later on, this work was further extended to mobile mammography, and it was published again in Census Journal in the year 2015. Now, based on the novelty and technical merit of this contribution, this work on non-linear filters, when presented in a conference, it was also attained a Best Paper Award. And after 2015, I had series of publications in this domain. And lastly, I mean, my entire research of past 7 to 8 years in this particular domain has been clubbed up, compiled, and published in the form of a book, which was published in January 2020 with the name Non-Linear Filters for Mammogram Enhancement. This book is published in Springer Studies in Computational Intelligence. So, to start the introduction part, coming to the computer-aided analysis of mammograms. Now, most of you would be aware, I mean, with the discussions which were made in the yesterday's sessions, and even some people would be aware prior to that also, that when we are talking about medical imaging or disease diagnosis, in terms of computer algorithms, we are focusing on 2 terms. One is CAD-E and another is CAD-X. So CAD-E is your computer-aided detection and CAD-X is your computer-aided diagnosis. Now, sometimes these new terms come into being, that is computer-aided analysis. So computer-aided analysis is a term which is, kind of a hybrid, or you can say a midway term between the two, where we are not waiting to go for the final diagnosis, but with the support of computer algorithms, utility of the machine, we are trying to improve the visibility of a given image, given medical image, mammogram, so that that medical image is so suited that it can be readily used for analysis and making diagnosis by a radiologist or a medical expert. So people would be aware of this simple block diagram of computer-aided diagnosis, where We have a repository of medical images which are subjected to pre-processing, then feature extraction. Now, extracted features could be selected just to, or you can say optimized to remove the redundancy. And then finally, it is given to a classifier. So now let's extend this particular block diagram to a more detailed one so that we can have an insight into each and every step of this computer-aided diagnosis. So computer-aided diagnosis is starting with the basic module, which is known as a pre-processing module. In the pre-processing module, first of all, what we are doing medical image acquisition. Medical image acquisition is basically like if you talk about X-ray images or the breast X-ray images, mammogram is acquired at this place. And mostly for computer-based processing, we are not going in for any real-time kind of acquisition. Rather, we prepare a pre-processed repository of the mammograms or the images in the form of a data set, which is then further used for pre-processing. So this medical image acquisition is now basically in the form of a data set of mammograms. Then we are doing some initial processing, some pre-filtering over here. After that comes the most important module over here. And this module is enhancement, where we go for contrast improvement of the medical image. Not just contrast improvement, we may go for noise smoothing also if there is certain noise which is taken place in the form of the medical acquisition process. Further, the image should be also sharpened. So to sharpen the images, there should be also some edge enhancement of these particular medical images. So something which you are referring by just one macro or one word, which is known as enhancement, I have tried to link it with three technical terms. One is contrast enhancement, another is edge enhancement, and a most important component which links the two, we will be discussing it in detail later on, that how contrast enhancement and edge enhancement is being linked with your noise smoothing or noise removal process. Then comes segmentation. So once the enhancement of the image has taken place, we try to segment the region of interest. Certainly, the unwanted area of the image is removed. Only the useful area, what we call as the region of interest for further medical analysis, that particular region is segmented. And with this, you are localizing the suspicious region. So whatever area which is suspicious in that particular medical image, or it requires a kind of further investigation or analysis, that part has become more localized for further analysis. So this particular set of blocks come under the head of what we know as the detection module. Now, generally, once we do enhancement or once we do segmentation, now at this step only, the image is well suited where it could be manually analyzed by a radiologist. So once this image is manually analyzed by a radiologist, then it is at this place what takes into being is computer aided analysis. So it is here where the radiologist or the medical expert intervenes, and he or she can make the analysis, direct analysis of these enhanced images for further decision making on those images. Then, if we want to automate this process further, because on one place, the medical expert himself or herself is doing the analysis just to find out the anomaly. If we want to do certain kind of a second opinioning on our images, just to find out, or just to, re-support or validate the decision which is being done by the medical expert or radiologist, we go for another module, decision support system, which is known as the diagnosis module. So here we are doing feature extraction, feature selection. Now, sometimes the selected features, the extracted features are so much that, or so many, that it requires to minimize the redundancy. So what we go for manual feature selection, or sometimes we tend to optimize the features or fuse the features. And later on, these optimized features are given as input to the classifier, which could be a machine learning tool, or sometimes we don't even use a dedicated feature selector if we are requiring a deep learning module at this place. So this is the diagnosis module. So what I highlighted in the beginning was that computer aided detection is the detection module over here, which is represented or acronymed as CAD-E. Similarly, the decision making part is the diagnosis module, that is your CAD-X. But some way, the main person is ultimately the human expert, the medical expert who's analyzing these images. So definitely the diagnosis module may give whatever outcome, but those outcomes have to be further validated by the medical expert before which any decision, any final decision could be made. So this is the entire setup of the computer aided diagnosis. Now, generally, when we go for, say, formulating research problems for our MTech works or our PG PhD works, generally the major focus of various individuals here is this, that we go for taking up or designing the complete module. That means our setup somewhere chosen is so huge that we take up the computer aided detection part also. We take up the computer aided diagnosis part also. So just to see that, we are working on an entire setup. We are starting from scratch with the input images till the time we are ending up with the classifier response, wherein, you are getting the accuracy of your diagnosis. So well in place, there is no anomaly when anyone does that. But certainly what happens that while doing this type of thing in our research analysis, generally our focus is majorly on the aspect that we want to do some contribution. We want to introduce some novelty. So generally what we tend to do is we change the segmentation algorithms. We change the different types of features. Whenever you have large number of features, we go for feature fusion or feature optimization, or certainly sometimes we change the classifiers, we cascade the classifiers, we tend to cascade some optimizer with the classifier just to tune in and get a better accuracy. But somewhere one bottom line is missed out, that we have a module in our initial stages by the name of enhancement. And sometimes every image in medical imaging is not a very good image from the scratch. If we take about very sophisticated imaging modalities like MRI or CT scan, images when acquired, they are very much itself in a good shape. They are almost in a better contrast to be used for further processing. But certainly, if you are picking up X-ray images, and that too X-ray images of a sensitive area, that is the breast region, they are generally very low dose X-ray images. And with these low dose X-ray images, the image which is generated at the point of acquisition is generally having very low contrast. The signal to noise ratios are very low over there. So because of that low dose of X-ray, low contrast, or what we say as the low sharpness, low resolution in that particular image, it is very, very difficult to detect some anomaly or the tumorous region or the cancerous region in those particular images. Secondly, another challenge is that whatever tumor, whatever initiator which we are trying to look in these images, they are generally white in color. Now the background tissues, generally the glands, the milk glands over there, they are also white. So sometimes even if if the contrast is okay, then also there is a problem that there is a white background, and again you are looking for something which is white in color in a nearly white background. So there is so much camouflaging in that at times it becomes very difficult to detect such nascent objects or such diagnostic features in these images. So what happens that our focus of research sometimes goes to development of, say, a CADI module, or say the development of a CADX module. We improve upon the classifiers. We are sometimes very happy with the accuracy that you are getting in the end. We are happy that we are getting a 90% accuracy. So definitely that is a system. And with these systems, certainly you have drawbacks also, that it is garbage in, garbage out. So if your ultimate image, which you are giving at the input, is not visualizing a particular anomaly, it is not visualizing a particular tumor, then is it truly possible to extract the correct features? See, features are extracted somehow because they are just mathematical descriptors. So initially, the initial processing is weak. The enhancement is not done properly. Now we are trying to extract from whatever region is highlighted before us. So definitely there is a fault, internal fault, while extracting features. And when feature extraction is internally faulty, certainly that is going to affect the accuracy also. So in this particular case, when we are talking about such X-ray images, which are, very weak in resolution, very poor in contrast, herein the primary focus lands into the domain where we are doing the enhancement. Because until and unless this particular abnormality is enhanced properly, visualized properly, there is literally no means of segmentation. There is literally no means of feature extraction. So once we are focusing on such category of images, then certainly it happens that the ready-made functions or the ready-made algorithms which are available in the repositories of our MATLAB or Python or different languages, they really do not work on these category of medical images, and it calls for development of more sophisticated filters for enhancing this category of images. So that is why when we are working on this category of medical images, there is a very strong emphasis to do research to develop filters for this particular domain where you are doing enhancement or where you are doing segmentation of your region of interest. So moving further on this, just there is a pictorial demonstration of what we have learned till now. Say this is a kind of an input mammogram. This is the mammogram. This is the pectoral margin. This is the outer margin. And this is certainly the tumor region over here. Now, if the tumor region is generally circular, we perceive that this is benign in nature, or this is not tending to be very harmful. But the moment we perceive over here the irregularity in the margins of this tumor, we see that there are some tentacles that are originating from this tumor. Then this gives us a direct hint, or it gives a direct hint to our radiologist that there is some kind of malignancy which is being originated in these images. So this is the response once we are doing pre-processing. We have done enhancement, and after enhancement, this particular region is the tumorous region is segmented. So our region of interest is segmented over here. So this is our detected region of interest. So this is the expected outcome when we look at a computer aided detection system or CADE. Now, from this detected ROI, what we see here, we tend to extract features. Now, features could be of different types. Here, just as a sample, I have shown these features, say, which could be statistical features like mean, standard deviation, contrast, correlation, energy, and homogeneity. Now, certainly, these may be too many features. I may have to make a selection of certain features. So maybe I have selected few features from here. Now, this selection could be a manual selection. It could be after some automated selection as a result of certain algorithm. So these are the selected features. Then these selected features are prepared in the form of a feature vector, wherein they are given to a classifier or a machine learning module, which could be ANN, SVM, or anyone, right? Where we get the final output as that the given mammogram is cancerous or non-cancerous, or a particular region of interest is consisting of a benign tumor or it is a malignant tumor. So once we are doing the final classification with the help of this artificial intelligence or this machine learning approach, this module is known as computer aided diagnosis. So what I discussed was the in-between thing, that was between computer aided detection and computer aided diagnosis. When we are getting an improved image, a radiologist or medical expert is trying to analyze that image on the screen itself to locate the suspicious regions, the tumorous regions, or the regions which are requiring some diagnostic importance. So how do we define or discuss computer aided diagnosis? It is using computerized algorithms for analyzing mammograms, which are identifying and marking the breast anomalies, right? Suspicious entities are marked, which certainly need investigation. And last but not the least, this everything is possible only when there is mammographic, when there is mammographic image enhancement, which plays a primary role in computer aided diagnosis. And once this enhancement part has worked in a legible manner, there are chances for early detection of the breast cancer. And it is actually the detection at this early stages can certainly is the only remedy to reduce the breast cancer mortality. So I already discussed that mammography is the breast X-ray. It is a low dose X-ray. And because of the low dosage of this particular X-ray, the noise levels are generally high. The intensity levels are 10 to 15%. And because of these deviations in the X-ray detector performances, what is affected in the final image is the very first thing that is affected in this image is the image contrast. Then is your signal to noise ratio. We have very low signal to noise ratios over here. And then the spatial resolutions, or what you call the sharpness of the images. So it is due to the outcome of the X-ray system. These three parameters of the image are severely affected. So that is why when we are doing enhancement, we are actually focusing upon contrast enhancement. We are focusing upon improvement of sharpness of the image in the form of the edge enhancement, and most important is whether we are improving the contrast or whether we are improving the sharpness of the image. We tend to see that the signal to noise ratio is not effective. The idea is to improve the signal to noise ratio during this process, and even at times, if that signal to noise ratio is not improved, the focus should be that it should also not be further lowered to what it was actually. So that is why, because of these three, lack of these three different properties in the images, mammograms are very different. They are among the most difficult radiological images which are to be interpreted by the radiologist. And that is why the analysis of these images is a very cumbersome task. And certainly that highlights the role of enhancement. Certainly when we are dealing with the enhancement or improvement in visualization of these mammographic images. So there could be different types of mammograms. Now, if you see different types of mammograms which are listed, shown on the screen, you see a fatty mammogram, which certainly appears little clear to visualize. Then you have a scattered fibroglandular mammogram, again, little clear only. Then there are two more cases where there is heterogeneously dense or extremely dense mammograms. And these are the category of mammograms where you see that the white patch density of the tissues is very, very intense in these two images. So what happens if I have, say, some tumor region located over here, but even if it is a white colored tumor located here, it is certainly easy to visualize over here. Even it is easier to visualize over here. But again, if some white patch is present in this region, would be certainly difficult to visualize because of the patch of these white tissues in the background. So what I talked about is the camouflaging of the anomalies. So again, the problem is more severe if we have an extremely dense background. So in this extremely dense white intensity background tissues, if again there is some tumor region or some small sized anomaly which is present over there, it becomes very difficult to identify such images. So definitely when we are processing these images, if we have these category 1 and category 2 images, certainly any types of algorithms could be helpful to operate on them. But if you are dealing with your category 3 and category 4 images, you really require sophisticated algorithms to work on them. So generally, if you read literature on this particular subject, you will rarely find very few works where, from the data sets that they have used, they are demonstrating their results on heterogeneously dense or extremely dense images. Rather, in most of the cases, what you will find that the focus of work or the focus of discussion is generally limited to the mammograms with the fatty tissues or with the scattered fibroglandular, because generally they are very easy to demonstrate results, but there are complications when you are dealing the samples of heterogeneously dense and extremely dense. Now, why we are understanding this? Because there is one more hidden factor over here, that is this tissue density actually thins out with the age. So actually, when you see the extremely dense breast mammogram, it means this is the mammogram of a younger lady, somewhere in the age group of less than 30 years. Once you go to heterogeneously dense mammogram, this is generally the age group of 30 to 35 years. And finally, a scattered fibroglandular mammogram is the age group of 40 plus or somewhere age group of 40 to 50. And again, the fatty mammogram is generally the age group of 50 plus. So if we see, this is the categorization of mammograms based on the background tissues, and there are variation in tissue densities with the mammograms with age. And you would like to relate one very common aspect, which maybe some of you would have also perceived in your nearby or in your neighborhood or in somewhere in your near families, that generally this particular cancer gets into picture or comes into diagnosis at a very late stage. So this is why it happens, because generally the outcome of this cancer comes or get to notice possibly beyond 40 years of the age. Just because, why? Because at that particular time, when you are doing the analysis, when you are doing the mammography, you are doing the ultrasonography, the tissues are very, very fatty, and in those fatty tissues it is very easily to picture out those tumors by the radiologist. But problem occurs when the female is in a very young age, and at that time, even if you get the mammogram done, it is very difficult to picture out that tumor region. So that is why we use the term that early diagnosis is the only remedy. Because had this tumor get detected at an age between, say, later 25 or say early 35 of age, there are very, very prominent possible treatment options which are present over there. But more and more, the tumor goes to the higher stages or the advanced stages beyond the age of 40. We are very limited with the treatment options. So this was the first part. That was the introduction of how breast cancer mammographic images, the different nature of the tumors, the different types of the breast tissues, mammograms, and the overall role of the computer-aided analysis, diagnosis, and detection is being discussed in the form of a overview. Now, landing to the more technicality of the topic, that is, let's, before migrating into the actual topic, that is non-linear filters, let's first quickly understand what is the understanding background of the linear filters and how they are comparing or competing with the non-linear filters. So if you talk about the linear filtering approach, then this is the very basic spatial filtering approach, or the windowing method, or sometimes you refer it as a box filter, is very much known to every one of us. So the working of a linear filter is such that, say if this is your input image, then a kernel or a window, say possibly of a size, the smallest size is a odd numbered window, that is a 3x3 kernel is taken. This kernel is actually convolved. There is a signal convolution over here. So this is convolved with this particular patch of the image. A kind of a averaging operation takes place. And once this averaging operation takes place, you get one value from here. And this particular value is replaced at, say, at one position in this particular image. Now, then the process is this window is currently centered at this particular position. Then you move this window to the next square, next pixel, and again the same convolution of the kernel takes place, and you get the next process pixel value. So this is the very fundamental spatial processing operation, which certainly most of us would be aware who would have studied image processing at their graduate or PG level. So now, if we see this as a local filtering operator, as I have said, that say if this is our input image. This is our filter mask, or what we call it, a filter kernel or filter window. Then actually what we are doing, we are carrying out convolution between our input image and the filter kernel. So if we are resolving it in the form of a discrete equation, it is somewhat like this, that is hi xn minus I, say from I minus infinity to infinity. This is for one-dimensional signals, and certainly if we are doing it for images, that is our two-dimensional signals, then this is denoting the pixel value, and this is denoting the kernel or the window which we are using for the operation. So these two are the basic signal processing equations, or the spatial filtering equations, which we are using for the mathematically for the linear filters. Now, these linear filters, sometimes you also call them the Gaussian filtering, sometimes you also call them as the low pass filter. So these filters are used in numerous operations, that is noise filtering, contrast enhancement, edge detection. But there are also certain challenges which are associated with these images. Now, what are these challenges which are associated with these images? They are that, first of all, they leads to image blurring when processed with non-Gaussian statistics. That means generally these linear filters are good enough when your added noises are very, very additive in nature. But certainly if you have different noise models which are superimposed, or you can say they are corrupting your images, which may be your say impulsive noise models, or you say your non-additive, or you say multiplicative noise models, then certainly linear filters are not a very good choice for processing those images, because in turns they cause blurring over there. Further, when you talk about medical images, then also linear filters are not the very good choice. We'll see why it is. And again, once we are talking specifically of say medical images, that is mammograms or the best x-rays, again, linear filters never becomes your preferred choice when working on these mammograms. So just you can see illustration over here, that say you have a input MRI image, and say this is the output image which is shown over here, then you see that the output image is clear, it is filtered off, but there is blurring in this particular image. Same is the filtering response in the image which is shown at the bottom. The first image is little more clear, which is actually the input image, but you say that after processing there is some quality is diminished, or you can say there is certain amount of blurring in this particular image. Now, beyond this, when you study image enhancement, there is one more concept that we should study in parallel, and that is human vision or human visual system. Now, what does this mean? So, if we try and recall, I mean, all those who have taken up digital image processing as a fundamental course, if we remember our fundamental books of digital image processing, generally the first or the second chapter discusses about the structure of the human eye. But most of us, generally as students, we tend to skip that particular portion, because we think that this is just a theoretical thing, this is just something biological in nature, and may not be very important to us. But I would like to highlight on one important takeaway of that particular area where we discuss the human eye or the human visual system. Now, it is known that the response of the eye to the changes in intensity of the illumination is known to be nonlinear. That means whenever we visualize something by our eye, the image formation process on the retina is actually following a non-linear kind of a pattern, or what we call it a logarithmic pattern. So this is the how the mathematically the intensity of image formation and how it is linked to the logarithmic of the image. So the image formation process, if you see that the how for someone for a given object the image is formed on the retina, then it follows a logarithmic pattern. And once we say that it is a logarithmic pattern, then we say that there is a feedback, there is a kind of a non-linearity which is associated in that particular system. So the similar concept is also imported from here for image formation with the display devices. So that is why this concept is imported from there, because once we look at the output of the display device, the perceived output is very similar to that, the one we see in the way the image is formed in the retina. So similarly, when the display devices are fabricated, when they are being formed, again, the same logarithmic image formation model is being utilized over there. So it is for this region what happens that many image processing systems are performed on logarithmic of the intensity values of the image rather than considering their actual pixel values. And this actually lays emphasis that this image formation process, or what you say that the image perceiving process, is actually non-linear in nature. So once this process is non-linear in nature, this justifies, or this gives an idea that non-linear filters are, that is why, much preferred if we are expecting some response, that the process response of a filter, if we are expecting, should be correlated with the human vision, should be pleasing to the human eye, then definitely the focus, the kind of filters which are used over there are the non-linear filters. So this actually justifies the utility that why these why non-linear filters are being utilized over here. So if we talk about the non-linear filters, what is better in these filters are when we are talking about their enhancement utility, when we are talking about their usage in terms of mammograms, that is the reconstruction here produces better visualization of the diagnostic features. Another is it can identify or evaluate the morphological changes. Now, what is to be understood at this point is when we say morphological changes, it means the changes in the shape or structure of objects in an image. So it is the utility, it is the best practice of a non-linear filter that it will also help to identify the morphological changes in the image. And when we say the morphological changes, we are linking it to the changes in the shape or size of the tumor. So again, if we are able to monitor that, say, I have a mammogram, say, which is taken on day 1. I have another mammogram which is taken after the 30th day, on 31st day, then definitely if the shape changes are very clearly perceived at the outcome of these filters, then definitely I can compare my image 1 to the one which is captured on the 31st day, that what are the morphological changes in those images, what are the changes in the nature of tumor in those two images, is the tumor grown, is in a growing mode further. So, this gives an impetus that this gives us a pre-idea that certainly the tumor is in growing nature, or it is trying to spread to other parts of the body. So the inherent properties of these filter to enhance bright as well as dark regions in the images. So this is another good property of these filter is that it can not only enhance the features which are there in a bright background, but even if you have features which are present in the dark regions, they are also tend to be localized with the help of these filters. So that is why these particular set of filters are generally preferred for processing of the mammograms. Now, if we see this pictorial demonstration over here, you can see that there is an original mammogram. With this original mammogram, this is the tumorous region which is shown over there. And if you minutely observe, then again in this tumor region, you can see there are some specks, they are tentacles, which are trying to originate from the periphery. It is not a very regular kind of a tumor which is shown over there. So this gives us a pre-hint, a pre-assumption that, this is going to picture out malignancy in some form or the other. Now, this is the way this image looks when it is processed with a linear filter, and this is how it looks when it being processed with a non-linear filter. So certainly you can see the change, you can see the betterment in the visualization when this is enhanced with a non-linear filter. Certainly what we learn in further slides, you'll get to know that even this image is also not a very good image. If you compare the typical expected responses which we expect in case of the mammographic images, but certainly to compare with the linear part, you can see this, that the enhancement with the non-linear filter is certainly much better in comparison to that with that of a linear filter. So this was an introduction again, where we compared the responses of the linear filter versus the non-linear filters. Now let's talk about the mathematical modeling of non-linear filters. Now, why I'm focusing on mathematical modeling of these filters? Because most of the times what happens that as a student, as a beginner scholar, sometimes our approach is that we try to look forward that we get functions or algorithms in the form of inbuilt libraries from our different languages which we are using. Now, the inbuilt functions, or the inbuilt algorithms, they can, serve purpose to a very limited means, but they cannot be generalized to different kinds of images. And so is the case when you are talking about medical images. And in again medical images, you are talking about a very specific category, that is the breast X-ray images, which are very poor contrast images. The sharpness and the spatial resolutions are low. The signal to noise ratios are also very low over there. So mathematical modeling, we try and understand that what is the concept of origination of those filters. So once we understand the concept of origination of these filters, that how this filter is being originated, with what concept this filter is being designed, certainly on use basis or in need basis, we can think of redesigning that model. We can think of customizing that particular mathematical model as per our particular requirement or as per the targeted outcome that we are looking for. Generally, very few people focus on this domain, because what is again our preferred choice is that we try to pick up some function readily from our inbuilt libraries, which could be directly applied for as a utility for enhancement or edge detection or whatever. So coming to the mathematical modeling of the nonlinear filters. So how this nonlinear filtering concept is originated, let's understand from that place. Then only you would be able to understand that how to modify these filters. So I'll be showing it to you in a step-by-step manner that how these filters are originated. Don't bug by this heavy mathematics. This is just for basic understanding. Once you understand it, it becomes very simple. And that is why when we try to, work with very novel contributions where, you are trying to come up something, design something in a new form of a filter, right? So this is only possible if you are changing the mathematical model of the filter, if you are changing the transfer function of that filter from the scratch, so that, you can have an altogether new performance on a given set of images, rather than what our current approach is. We just try to pick up a filter from the library. We just tend to, tune the values. We just change the window sizes and try to, somehow adjust to the kind of response that we are getting from. So just to get an idea, the non-linear filters are being originated from very common series, which is known as the Taylor series. So this Taylor series, sorry, is somewhat in this form. Say y is equal to fx, this is 1 plus x, then x square upon 2 factorial plus x cube upon 3 factorial, and so on. So if you see this particular series, you can see this is a constant part, this is a linear part in this series, and this is, say, the square part, or you can say the quadratic part of this series. Then if you see the another one, this is the cubic component of that series, and so on. So this is a kind of a nonlinear series. But generally, if you see this particular series, the outcome in the form of implementation, like suppose if nonlinear filters are developed with the help of this particular series, there has been slow convergence and design complexity. So generally, the origination of these filters has been from Taylor series, but not brought much into practice. So there is another series where which, you get a more clear picture of the nonlinear effect. And this particular series is known as the Volterra series. So if you see this particular series, again, this is a constant part which we see in this. Then again, this is, you can see the variable part where this is HL and XN. So somewhat, if you are going to expand this part, this will come like this, that this is HX, then say square, then say, suppose this is H1, this is H2, this is H3, this is X cube, and so on. So this is how this particular series gets expanded. So you can just have a look that this is the constant part. This you can observe as the linear part of this particular series. If you see this part, this is the quadratic part of this series. And if you see this part, this is the cubic part of the series, and so on. So this is how, or what looks like a Volterra series. So now our another focus is that how we are going to use this particular series for designing filter, because our aim is to somewhat design a non-linear kind of a filter. So if you just see this series, this is an unending infinite series. So what we go for truncation of this series. Now it depends that where we are going to do the truncation in this particular series. We get to know the level or order of the filter that you are getting at the outcome. So over here, as you already aware that this x or xn minus 1, xn minus j, they are just showing you the input part. Then h is actually the Volterra kernel, or somewhat you call it the filter coefficients. But there is one observation over here, that as and as you move at a higher component in this particular series, what is happening? The number of coefficients are going to grow exponentially. If you see, the number of coefficients are going to grow up this with the increment in the order of the filter. So the coefficients are going to increase, and the moment the coefficients are going to increase, you'll feel more and more complexity in practically designing such types of filters. So there is a requirement to truncate this particular series so that you can design different form of filters. So you can observe that suppose we are truncating this series in the manner that you are just getting this at the output. So now my output will be just yn is equal to this part. So that means what we are getting at the outcome, this is a linear filter. Now suppose I'm truncating this series in this manner that I'm just getting this part at the output. So this is nothing else, but this becomes your quadratic filter. Again, in the same way, this is going to give you a higher order filter or a cubic filter, but generally it is advisable that not to go beyond this point, because again, you have increment in the number of coefficients, and with the increment in the number of coefficients, you are landing into the trouble of other things like convergence issues, or you can say the design complexity. Then comes another name, which is known as a Volterra filter. So again, a very related name, since the filter is derived from Volterra series, therefore the name is Volterra filter. Now, generally, this is a filter. What is different about this filter is that we are picking up this filter in such a manner that we are picking up the linear term also in that filter and quadratic term also in this filter. So this filter over here will be a combination of a linear filter and a quadratic filter. So you name this particular filter as Volterra filter. What is different from these other three filters is that other three filters were having just one component in themselves, that either it's a linear filter or it's a quadratic filter or it's a cubic filter. But over here, the Volterra filter was a combination of linear filter and the quadratic filter. So the later modified version of this Volterra filter is known as the polynomial filter, which is being developed by me and my team for utility on mammographic images. So if we see the response of, say, we have already seen the response of a linear filter. So if we see how does a quadratic filter response is taken up on mammographic images, you see that this is the response. So definitely enhancement is there, better visualization is there. But what we see is, say, this is the original image. This was our tumorous region. So this is actually our input region of interest, and this is our enhanced region of interest. But what we notice is that the enhancement has taken place over there. But here what you see that this is over whitening is observed. So when we see over whitening, that means what has taken place is the saturation of intensity levels. And when these bright saturation level, bright intensity levels are saturated, so actually this over brightness is referred to as noise, or what we say that intend to increase the contrast, your filter is trying to increase the noise also. So this becomes actually the drawback of this particular filter, that during mammographic image enhancement with your conventional quadratic filters, it is coupled with amplification of unwanted noise. So the filter was trying to improve the contrast of the pixels, but in that task, somehow the noise has also got enhanced, or the noise has also got amplified. So again, this becomes a challenge working with these quadratic filters. So now again, if we compare linear versus quadratic filters, then we can see that again, this is our original region of interest. Then say this is the linear filter processed region of interest, and this is the response with that of a quadratic filter. So we can see that definitely in comparison to linear filter, the response of quadratic filter is much better, but somewhere quadratic filter is suffering with other ailments. Like you can see that this particular area somewhere, you can see blurring in this particular region also, right? Somewhere you can see over enhancement in certain regions also. So these are all the ailments of a quadratic filter, but somehow this is better than your linear filter. So what is the conclusion over here? That when we go for mammogram enhancement, our requirement is not just to enhance the contrast, but to enhance the edges also. So when we say enhancement in mammograms, we are referring to both contrast enhancement and edge enhancement. So this is how you are getting enhancement with the linear filters and with the non-linear or your quadratic filters. Now, let's talk in specific to our next category of filters, which is known as the Volterra filters. So as you see, linear filter response we have seen, quadratic filter response we have seen. Cubic filter we generally don't prefer because again, more number of coefficients, problems in designing. So we are not discussing or taking up cubic filter because again, it is not preferred much for practical applications. So our definitely immediate next choice of working is our Volterra filter. And what was different about these Volterra filters were that they had a linear component also, a linear filtering component was also present, and you also had a non-linear or a quadratic component which was also present in this filter. So you generally term it as a second order Volterra filter. Why we are terming it as a second order Volterra filter? Because just have a look that if we see here, so this is L is equal to 1 and this is L is equal to 2. So generally when you are truncating the series in a cumulative manner up to L is equal to 2, this actually becomes your second order Volterra filter. Here L is equal to 1 and L is equal to 2. Both components are being considered. And in fact, the L is equal to 0, that is this constant parameter is also included as one component in the Volterra filter. So you are terming it sometimes as a second order Volterra filter. And this is how, I mean, the characteristic equation of this filter looks like that this is your constant terms, this is your linear term. So H theta denotes your linear coefficients over here, and H phi denotes your quadratic coefficients of the particular filter. So this is the characteristic equation of your Volterra filter. So if we expand this particular characteristic equation, you can see that this is your linear component and this is the quadratic component of this filter. Of course, there is one constant term or somewhat you also call it as the offset parameter of the given filter. So generally, for designing such filters from mathematical point of view, you require one set of linear coefficients and another set of quadratic coefficient. So another part, say suppose the basic kernel size for linear filter that we select is 3 cross 3. That's the basic size. So that means if I see the number of coefficients that is required for the linear component is 9. Now, it is generally said that if you have n coefficients for the linear component, then you require actually n square coefficients for the quadratic component. So that means for the quadratic component, the number of coefficients will be 9 cross 9, that is 81 coefficients. So that means when we are mathematically determining this particular designing or determining this particular filter, so once you design this filter, the next task is to determine these coefficients, just to have an idea that what should be the processing kernel, what should be the processing window for this particular filter. So for this linear part, you require 9 coefficients, and for the quadratic part, you require 81 coefficients over here. So what is good about these two components? That means we have said that rather than picking up alone a linear filter or a quadratic filter, we have taken a combo where a linear component is also there and a quadratic component is also there. So what is good is that the linear component is operating as a low pass filter. So sorry. Then the quadratic component is acting as a high pass filter. So what is good is that this filter is now working as a combo of your low pass filter and your high pass filter. Now certainly low pass filter has its own benefit in the form of providing noise smoothing effect. Now what is good about noise smoothing effect is that somewhat if your quadratic component is going on to provide contrast improvement, then what we have seen that once contrast is enhanced with the help of a quadratic filter, it also tends to enhance the noise. We have seen it previously in the response of a quadratic filter. But now in combination, you have a linear filter over here. So this linear filter will try to suppress the noise enhancement part, which will come due to the outcome of contrast enhancement with the quadratic filter. So it is this noise smoothing effect will be provided by this linear filter. Then again, quadratic filter had another benefit also, that apart from contrast improvement, it is also providing detail preservation, or what we call it the edge enhancement. So this is what I have already told you, that how we are finding out or numbering out the coefficients for your linear filter and your quadratic filter. So now that was about your Volterra filter and its structuring, its mathematical part. So let's find out now what are the challenges and research gaps when we have studied non-linear filters so far. So if you see the response of this Volterra filter, then a very important constraint which is brought to our notice is that, so this is our original mammogram, this is the original region of interest, and this is the enhanced region of interest. So if you see the enhanced region of interest, what happens that I have a linear component, I have a quadratic component. Now suppose your quadratic component is more dominating in nature, then what will happen? It is going to enhance the contrast, which is visible that the contrast is improved over here. But again, it will also tend to amplify the noise. But since the linear component is now not very dominating, what will happen? It is not going to, exercise very big control on the noise enhancement or the amplification part. So certainly this type of an image is obtained. So you are categorizing this as what is known as the contrast enhancement constant. Now, see another thing. Suppose we are now trying to do edge enhancement with this filter. Now, if we are trying to do edge enhancement with this filter is trying to sharpen the edges with the help of the quadratic filter. But suppose now the linear part is more dominating. So if now the linear part will dominate more, it will try to smooth out the noise. Now in the task of smoothing out the noise, what it has done? It has now blurred the edges. So you are trying to sharpen the edges, right? But now the linear component has become overprotective. It has now diminished the edges. So now actually the visual quality of the edges has got diminished. So this is what is known as the edge enhancement constraint. So this is one very big trade-off with your Volterra filter, or what you call it as a non-linear filter, that you have to, design your linear and quadratic filtering parts in such a manner that you have a very balanced compromise between these two trade-off. One is the contrast enhancement constraint and another is the edge enhancement constraint. And that is why we say that when we enhance the mammograms, it is not just about the enhancement of contrast or the sharpening of the details. It also requires a noise smoothing process, which should be there in a balanced manner. So this is one challenge, one trade-off when you are using non-linear filters for mammographic image enhancement. Then comes another thing. Now, if you look at this particular mammogram, you just have a vague idea that this is some tissue density which is being located over here. Now, if we extract the region of interest over here, if you try to have a very closer look over here, what you see that there are some tiny white dots which are present over there, right? These white dots. So these white dots are actually the calcium deposits, and they are the very, very prime initiators of the cancer. That means once these calcium drop, these calcium small dots, they are scattered in nature, they slowly get congested, they cluster up, and later on they change the shape, cluster up into a small tumor. So this is how the growth pattern of the tumor occurs in the mammogram. So again, if we focus upon early detection, right, actually you have to be very vigilant while enhancing these micro calcifications, right? But again, when we are trying to enhance these micro calcifications, you can see the over enhancement over here, right? Now, because of over enhancement in certain regions, again, these calcifications are visible, but not to a very good extent. And now if you try to apply the enhancement in a more strong manner, what has come? See, again, oversaturation and noise has come. So whatever visibility was certainly there, it has now also got diminished. So again, another challenge which is associated with these Volterra filters is that they are not really not good enough for visualizing the initiators of the breast cancer, which are the micro tiny calcifications. They could be very good enough for visualization of the grown-up tumors. But if the tumors are very much in the initiating stage in the form of calcium deposits, they are certainly not to be properly amplified with these Volterra, not to be properly visualized with these Volterra filters. This is another challenge. So another thing. Now we have seen that this Volterra filter is having a linear and quadratic component. Certainly it is good in one extent that one part is working as a low pass filter and one part is working as a high pass filter. Now, what we want that there should be a compromise between noise smoothing and contrast improvement, right? So once contrast improvement is there, noise smoothing should be also there so that the undesired noise amplification could be stopped. So that means this is nothing else. What we are talking about is your contrast improvement constraint, and another is the trade-off between noise smoothing and the preservation of details. What you are referring to is your edge enhancement constraint. So what we conclude is that when you are enhancing the mammograms, we are not just improving the contrast, we are not just improving the edges, but we are doing noise controlled contrast and edge enhancement, which is actually difficult to be achieved. So there is a requirement that this non-linear filter should be in a much improved form to provide the desired expected outcome on the mammogram. Now, another challenge with these non-linear filters are that sometimes when they are deployed, they are not yielding very satisfactory outcome on medical images. Now, why it is so? The reason is, number one, the image background varies greatly with different types of tissues. So I have already discussed this point that you have different category of age groups, and with different category of age groups, there is a variation in the tissue density. So definitely a filter can give you very good response when you have a fatty tissue in the background, right? That means the mammogram of the age subject where the age group is above 40 years. But again, this particular filter may not give you a very good response once you are using it for the age group of 30 or less than 30, where the background tissue density is very high. Another problem with these non-linear filters is the noise amplification. And again, if you are trying to improve this noise amplification, sometimes it obscures the margins of the tumors, right? Another constraint with the non-linear filters is the kernel size and the number of coefficients. So definitely, say, finding out 9 coefficients of the linear part is very simple. But again, once you have to find out the 81 coefficients of the non-linear or the quadratic kernel, actually, it's a very time-consuming task. So with these non-linear filters, these were the challenges that we have seen. Now, what is the kind of the expected outcome? That means what we actually want from this filter, this should be clear. Then only, we can map up that what is missing in between, and we can develop a new category of filters, which we'll be discussing on later, is your polynomial filters, right? So with this mammographic enhancement algorithm, it is expected to improve the contrast between the region of interest foreground and the background. So our first requirement is that it has to improve the contrast of the foreground with respect to the background. So sometimes it is to be understood that maybe because of increasing the contrast of the foreground, what is happening? Noise is getting enhanced. So sometime to improve the contrast, we can also suppress the background. So if we tend to suppress the background, the foreground will be visible on its own. And secondly, you are waiving out the risk of noise amplification during that process. Secondly, sharpening of the lesion edges or the edges of the tumors, because once there is sharpening, then only you can clearly visualize that whether the tumor is properly rounded or there are diminishing boundaries, and it is actually the change in shape of these boundaries. This is only how a radiologist tend to predict the growing stage of a particular tumor. So again, sharpening of the boundaries is a very much necessity when we are developing a mammogram enhancement algorithm. And another one is control over noise enhancement and blurring. So this is the outputs that we have seen with this kind of a filter in the form of the contrast enhancement constraint and the edge enhancement constraint. But now, if you have a look at this particular image, this is actually the expected outcome. Now, how could certainly this be achieved? Now you can see the foreground is there. You can see that you have very good contrast of this foreground. Now this is only possible when there is background suppression, because this foreground is appearing better only because the background has got suppressed. And you can also mark out the sharpness of this particular tumor region, because now these boundary, the disturbances in the boundary, the tentacles, they are very, very easily visible in this particular image. So this is the expected outcome, what we look forward when we are designing a mammogram enhancement algorithm. So now the new contribution which I have worked out to improve these Volterra filters, this is your non-linear polynomial filters. Now, certainly why I gave you that much background, so that you can try to understand that how the change in the mathematical structure being made, and how that you will see that how that will land out and provide an entirely different kind of a filtering structure with a very, very improved kind of a response. So if you talk about nonlinear polynomial filters, in short, you will see that at many places during this lecture, it will be referred in short as NPF, or your nonlinear polynomial filters. So now, as we know that they are the second order truncations of your Volterra filters. So this is the kind of the structure. So if you see, the basic structure of this particular filter is same as that of your Volterra filters. Now, what is different in this filter? Now you see. So if you see what is done now, over here, there are some weight indices which are introduced in this filter. One weight indices is known as gamma, and another weight indices is known as lambda. So gamma is the weight index which is used in the linear part, and lambda is the weight index which is being introduced at the quadratic. Now it is actually these weight indices, you will get to know, which are being deployed to control the different situations, the different trade-offs which we have come to discuss so far. That means the contrast enhancement constraint, the edge enhancement constraint, all these things are very much controlled by including these two weight indices, that is gamma and lambda, into this particular filter. So we are already knowing that this linear component is providing the noise smoothing effect, and the quadratic component provides for contrast improvement, detail preservation. And now you see that one more thing is there, that because of these weight indices, there is also compensation for blurring. Because earlier what we have seen is that somewhat you want to do detail preservation, due to noise smoothing, you are losing those edges. But now this control over blurring is also being associated with these new weight indices which are introduced in this particular filter. So this is the linear and the quadratic component of this particular filter. Now, as I already told, that this gamma and lambda parameters, with this you can exercise an adaptive control in enhancing the image details while also smoothing out the noise. So how we are selecting the values for gamma and lambda? Then again, there are certain techniques which have been taken to select those values. That means, say, suppose we take the example of a smallest possible kernel, that is a 3x3 kernel. Then over here we see that if the coefficient is there at the particular center of that particular kernel, right? Then over here, you are selecting it in the form of A, right? If you see it is B, then it is for the positions which are located at the add locations. And if the positions are at the even locations, you are naming it as C. So with this, you can see I'm skipping some of the mathematical steps in between. So we actually come to three different categorizations of this particular filter. One is known as the type 0 filter. Another is known as the type 1 filter, and next is known as the type 2 filter. So you can see these A, B, C, these components taken over here. So you can see that the center component, that is the fifth pixel, is over there. A is being taken as the power indices, then 1, 3, 7, 9. At these positions, B is being taken, and say at 2, 4, 6, and 8, at these positions, C has been taken. So this is how you come to get three different component of this filter, which is known as type 0, type 1, and type 2 filter. So again, doing experiments with different components of this filter is again a massive research into this. Now, from this internal analysis, what we have come to know that the type 0 filter, when applied in isolation, it had certain types of benefits. Now, what were the benefits of this type 0 filter? Now, type 0 filter gave very good output on the mammograms with fatty tissues, right? It provided noise smoothing during contrast enhancement and also reduced the blurring of edges. These were the benefits of the type 0 filter. Now, if you see the type 2 filter, now type 2 filter gave very good response on the tissues when there are glandular tissues or when there are dense tissues. So if you remember, we had category 1, category 2, category 3, and category 4. So I showed you 4 images. So certainly for type 0 filter is giving you very good response when the images are of category 1 and category 2, right? But when you have heterogeneously dense or very dense images, then that response is very good with the type 2 filter. Then again, sharpening of features is very good with this particular filter. Delineation of boundaries is very good with this filter, and background suppression is also very good with this filter. These two things we conclude once we have applied these two filters in isolation. So now, what was actually a betterment solution over here was, so why not to fuse the responses of both these filters? Because once we are trying to fuse the response of both these filters, we are going to have a universal filter where you can see you are able to process all types of mammographic images, whether the background tissue is fatty or whether the background tissue is glandular or whether the background tissue is dense. All these kind of images you can process with this combination of type 0 and type 2 filter. Now, whatever shortcoming which is being left over in a type 0 filter response, it is actually being overcome with the usage of type 2 filter response. So that is why once you are fusing these two, whatever complementary things are left out at any of the response of any of the filter, it is actually make up in the response when you are combining these two filters. So that is what we have done over here. It's a linear fusion or a linear combination of type 0 and type 2 filter. So this is what we have done here in this work, and the work which you will refer, that is the initial paper of IEEE Census Journal, is actually based on the response of the combination of type 0 and type 2 nonlinear polynomial filter. So if you see, then this is the general block diagram of this particular approach, of this particular framework, where we see that there is a digital mammogram database. I'll be talking about this database lately. Then you are doing some pre-processing. Then you have the response of type 0 polynomial filter, type 2 polynomial filter, and finally you are fusing these two to get the enhanced mammogram. So just a small demo can be seen over here. If you see this particular image, this is the response of type 0 filter. This is the response of type 2 filter, and as a combined response, you get this kind of a image over, right? So you can see a very well enhanced and a kind of a segmented region of interest is obtained at the output of this combination of type 0 and type 2 polynomial filter. Again, another example, if we see, then again, this is the response of type 0 and type 2 filter. So with the fusion, this is a kind of response is observed. So if you see this response, you can very easily locate that this is the shape of that particular tumor. And then at the background, if you see, you can also locate that, there are certain calcifications which are also highlighted in the background of this particular mammogram. Then once we are processing these enhancement outcomes, we also expect that, there should be some very defined quality measures, performance measures, which should be available with us for adjourning the quality of these particular images. So as we are, focusing more on towards the filter design and the responses into this session, I won't be discussing much about the image quality assessment of mammograms. Only I'll be focusing upon directly that what all are the parameters which we are using over here. So now, the image quality assessment measure that we'll be using for mammogram enhancement evaluation in this particular work is contrast improvement index. So as we have seen that our focus over here has been to enhance the foreground and also to suppress the background. So if you see over here, then there are the expression for contrast computation that is used here is C is equal to F minus B upon F plus B, where F indicates the gray level of the foreground and B indicates the gray level of the background. So you are calculating in this manner the contrast of the original mammogram. Then you are also calculating in this manner the contrast of the enhanced mammogram, and then you are dividing the two, that is the enhanced mammogram upon the original mammogram. So you come across a metric which is known as the contrast improvement index. So you get a whole number value at an output of this particular metric, and higher the value of this particular metric, it indicates better is the response in terms of the mammographic image enhancement. Now another two parameters over here which are being used are PSNR and ASNR, that is peak signal to noise ratio and average signal to noise ratio. I mean, any one of the two could be used. Sometimes you use both of them, or at times just PSNR alone is sufficient to use these as parameters. So if you see, this is C, then C is actually denoting the pixel with the highest gray level intensity. Then over here, this is the average gray level of the background, right? And S over here is denoting the standard deviation in the background of that particular image. So this is how you are calculating the PSNR. Only difference over here is in the bottom formula. These two parameters are same. Only the difference is this, that here you are taking the peak value of the foreground, and this is the average value of the foreground. So once you take the peak value, it is known as peak signal to noise ratio, and once you take the average value, it is known as the average signal to noise ratio. Now, a question arises over here that we are tending to see mammogram enhancement. So once we are evaluating mammogram enhancement, I think contrast improvement index could be a sufficient metric. Then why we are evaluating peak signal to noise ratio and average signal to noise ratio? Then the answer is that we also have to check that during enhancement, it is not just necessary that the contrast is improved. We also have to check that during the enhancement, it is not trying to enhance or amplify the noise. So if noise is amplified there, right, then certainly your PSNR value will be lowered. And if noise is improved, noise is not enhanced, or that component remains stable, your PSNR value will be, better. So this is how you're going to find out. If you are seeing lower values of PSNR, that means you have noise amplification. If you have high values of PSNR, that means your signal to noise ratio is improved in the particular output image. So now, if we run simulation on these particular images, then the first thing is what we should know is that where we are getting the input. So regarding the mammogram research repository, there are certain very common data sets, very common mammogram databases, which are being used for processing these input images. And they are these three common databases. One is the MIAS, that is the Mammographic Image Analysis Society databases. This database is being collected and prepared by the University of Essex, UK. There is a dedicated research group associated with a hospital over there who have, contributed and collected these mammograms. They have digitized these mammograms to be used freely in a public domain for different research. So if you are working in the domain of mammograms, certainly you cannot escape to use these two databases. Another is your digital database for screening mammography, that is DDSM. This database is being prepared. It is being populated by University of South Florida. And again, 2 or 3 different hospitals were clubbed up with them for contributing these images. So again, when you are doing literature survey or you are referring to different papers in this domain, you see that some of the papers have focused on mini MIS database. Certain papers have focused on both these kind, that is DDSM and MIS. And even I have whatever images I have shown you in this results or at different places, they have also been taken from this mini MIS database or this DDSM database. So now, although they are little old databases, right? Say up till year 2000 databases, but they are very strong benchmarking databases. So these benchmarking databases are certainly used to compare our results with that of any of our previously published works where you want to compare the results. Another one, which is say it is little recent, that is your B-Screen or the Bayesian Decision Support and Medical Screening Database. This is another one. And remaining information on these different databases you can get from this particular web link, that is www.mammoimage.org, where you get an idea or links of different types of mammographic image repositories which are to be used. Now, in the recent trend, because these two databases are generally to be used for benchmarking, in the recent trend, what is being done is, what people do is, all those who select to work or research in this particular domain of breast cancer detection, they try to collaborate with some hospital or some path labs which are working on mammography or these digital x-rays, and they try to populate their own data set for the analysis. So this is the recent trend, that these two older databases, that is MIS and DDSM, they are being used for comparison, benchmarking and validation of our results. But again, as to see the applicability of your approach on a very new or say certainly live cases of breast cancer which are being under treatment with some doctor, it is always advisable to, at least if you are not able to create your own repository, try to, if you are working in this particular domain, try to get associated with some specialist, some doctor into that area, or some good hospital who can contribute and tell you or provide you with some real cases who are currently under treatment, the treatment process is under progress or currently under medication, where you can take on those cases, apply your filters, apply your algorithms on those, and then certainly those results in turn are no small works, but actually they become an entire case study for publication in the form of a research paper. Because trust me that apart from these benchmarking databases, if you are picking up, say, a handful of even 5 to 10 cases, very good cases, where you can see, show or prove the, demonstrate the utility of your algorithm or your work on those particular images, I mean, each one of the image becomes a separate case study in itself. So this is a very recent input which could be incorporated for all those who are started their research in maybe this particular domain or in some other domain of medical imaging. Just try it. Do not I mean, you have numerous databases which are available at your disposal, but try to get some new cases from your vicinity with some doctors or some labs, so that some live case work, some live demonstration, new case studies could be incorporated beyond those which are already being discussed numerous times in different papers which are being published so far. So for here, the results which I'll be showing you, they are on from the MIS and DDSM database. So you can see over here, this is the first thing during the simulation. We have to select the mask. So mask is actually your window size, the kernel size. So again, the kernel size as prominent, it could be a 3x3 kernel, but it could be a 5x5 or it could be a 7x7 kernel mask also. So if you see over here, then this is the response which you have obtained with the 5x5 mask, which is certainly better, you can see, in terms of enhancement with that of a 3x3 mask and a 7x7 mask. In a 3x3 mask, the contrast enhancement is not very pronounced, but in the 7x7 mask, you can see the contrast enhancement is there, but again, the blurring has started due to certainly the increment in the mask size. So if we see the performance parameters, again, it is also validated that you can see with the 5x5 filter kernel, you can see that the CII value is the highest, and that too, the other two parameters, that is PSNR and ASNR, they are also better with this 5x5 mask. This is another image which is being taken from a DDSM database. This is the response of a 5x5 mask. You can see that there is tremendous blurring, which is there in the response of the 7x7 mask, and there is less background suppression when you see the response of a 3x3 mask. So again, you can see better values of CII, PSNR, and ASNR when you get a 5x5 or when you use a 5x5 mask. So with this, we have made a selection that for all the simulations which are being used, this 5x5 mask is being used for simulations. Now, determination of these values was again a hard task. So these were the values which were determined. Then this is how the ABC values have been selected. Lot of simulations have to be done so that you have to find out that what should be the suitable range to tune out the range of these parameters, right? So once you get a tunable range, you apply this filter on these images. So you can see this is the original mammogram with a fatty background. This is the enhanced mammogram. So this is the region of interest you are getting. And these are the possible values of CII, PSNR, and ASNR, which you are getting over here. Again, this is how the region of interest you are getting. These are the value of the quality parameters. Again, this image you can see, you have a foreground tumor, and in the background you have different calcifications which are clearly visualized. These are the values of the quality parameter. Now again, this is a trivial case where now the background is fatty glandular. So this is the original mammogram. This is the enhanced mammogram. And you can see the tiny microcalcifications are very clearly visible over here. Then this is one very good example where there is a heterogeneously dense background tissues. This is the enhancement which is received on the dense background, right? And these are the quality parameters. So generally, what happens that while you are selecting these values, sometimes you have a lower enhancement. Sometimes as you increase the value of these parameters, there is very good background suppression. So what is advisable is that we should have a kind of, tunable filter, so that for computer aided analysis, your radiologist or medical expert is getting a proper tunability option at the screen, so that, depending upon at what particular scale they are getting desired visualization, they can use that particular scale. Because, at times it is not all the time possible for the end user to change the values of the filter, right? See, understand from the user point of view that he or she is not an engineer who is running the simulations. So it is better to take a proper tunable range of that filter, and that tunable range is given as a slider over there on the front end. And now the radiologist can move the tunable button, and with that he or she can see the level of enhancement which is required, the level of enhancement which is required to see the background, that could be certainly seen. So here is one example. Say when you are selecting one particular value of the parameter, this is the output that you are getting, right? Say now the value is changed, again the filter response is changed. Now again you see the background is getting suppressed. Now the background tissues are also visible. The edges have now started becoming more sharp. See, another change in value. Now again the edges have become more sharp. See, the sharpness is increasing. Now the background is getting suppressed. See, now we are moving towards a clear demarcation. Now nearly a segmented tumor has obtained. So you have all the different scales available with you to generate the desirable image which is required by the radiologist to make the investigations, to report the findings. So if we see the simulation results which are obtained over here, you can see the response of type 0, type 1 and type 2 filters which were originally executed, and then the proposed filter is a fusion of type 0 and type 2 filter over here. So definitely you can see that the CII response is better than any of the individual filters, right? See, if you see the case number C, you can see that with type 0 filter, the highest value of CII which is obtained is 5. But with this combination, the highest value that you are getting is 6.7. So this shows the utility of this combination of particular filter in comparison to the original counterparts of this particular filter. This is, you can see as the comparison of results from different techniques. So you can visualize that the proposed nonlinear polynomial filter is giving a better enhancement response in terms of the other techniques. This is one sample for the dense background. You can see that the quadratic filter is showing over enhancement over there. Unsharp masking is showing a different kind of a response, but a very clear segmentation of the tumor is obtained. A very clear visualization is obtained with the nonlinear polynomial filter. Right? So we are concluding with this discussion that type 0 polynomial filter has certain utility for fatty. Similarly, type 2 is performing well on other types. So therefore, you are combining the responses of type 0 and type 2 polynomial filters over here. Now, generally, the analysis of a medical image is not complete without the final validation by a radiologist. So it is always advisable that you should not be just happy in running your own quality metrics and obtaining the results just to satisfy your engineering capability, right? Ultimately, the end user for those images is a medical person. So until and unless that medical person is going to validate and say that this particular image is better for their analysis, our task is not done, even if you may get a very high value of CII. But if the radiologist says that, sorry, this image is not very good for us, then definitely we have to rework, we have to reiterate the parameters to find out that where are the gaps, right? So see, on certain set of images, these were the mean opinion scores which are received from the radiologist on the original mammogram and on the enhanced mammogram. So certainly all responses are not always good in the type of opinion scoring, but if you are getting say nearly 90%, 80% ratings on certain of the mammograms, we can presume that somewhere there is a balanced correlation between the objective quality metrics that you have used by formula and finally the end users, that is your radiologist. Now, coming to the future research directions, because still there is a lot of scope in to work and do further research to formulate further research problems in this particular domain. Now, if you see, first is the quality of enhancement may be controlled by optimal selection of NPF parameters. Now, right now, these different filtering parameters are being auto-determined, manually tuned, and then selected. So now what is the remedy? That these filter parameters could be optimized with the help of some good optimization algorithm, maybe genetic algorithm or some any other algorithm you can apply to optimize these parameters. So certainly the tunability for this particular filter can be expanded or can be sorted out rather than extending it to different types of ranges. Another thing is that you can combine these nonlinear polynomial filter with the multi-resolution approaches, because we have different types of other approaches. Say you have a wavelet domain, you have contour-led domain, you have shear-led domain. So there could be a possible option that you can first convert your image process your image through a wavelet filter, and then your decomposed images can be treated with these types of filters for a better outcome. Then this nonlinear polynomial filters can be combined with other image processing approaches like unsharp masking also. Then a most important thing, this is performance evaluation of mammogram enhancement and the approaches. Now, generally, if you talk about the image quality assessment of the mammogram, since the discussion of our today's lecture was most focused towards the nonlinear filters, actually image quality assessment of these mammograms is a more focused area when you are talking in specific to the simulation part, and it is a complete lecture of 2 to 3 hours if you are discussing image quality assessment and different metrics which are used or designed specifically for mammograms. So again, this is a hint for all those who are working on medical images. It's my very sincere advice that once you are working on medical images, don't just try to narrow your thing to the available quality metrics which are available for ascertaining the quality of the image. You should also find out that you should also know that at times maybe one particular quality metric could not be a very good one for assessing the response of a particular enhancement image. Getting it? So maybe you are doing mammogram enhancement and you are using mean square error. So certainly try and understand mean square error could be a very good metric when you are using general images to find out the error, right? And from that mean square error, you can calculate the peak signal to noise ratio in decibels. But try and understand mean square error is a very good metric when you have an ideal reference image, you have a filtered image, and then you compare your filtered image to an ideal reference. Then at that particular time, you are getting the error with respect to the original ideal reference image. Now you see the example of mammograms. In mammograms, your original mammogram is actually a poor quality image. Now your enhanced mammogram is a better quality image. So if you want to compare the quality of your enhanced mammogram and you will take the reference as your original mammogram, you will never get the correct answer. And maybe while running those matrices, you get demotivated saying that, the error is coming so large. Obviously, it will be too large because your original image is not a good image. And you are comparing your good image, which is there at the output, with a faulty image. And then you are bugging why the error is not reducing. So please understand that you cannot just rely very blindly on any of the metric. So definitely, exploring and finding out a dedicated metric for a particular image processing operation specific to medical images is again a challenge and a compare and a huge research problem. Specifically, if you talk about mammograms, there are very few metrics which are dedicated metrics to be applied on mammograms. So if somebody is trying to work or research in this domain, then certainly designing a dedicated quality measure for the enhancement of mammograms or to evaluate the mammogram enhancement is itself a very big problem, right? It could be such a huge problem that it can cover two objectives of any PhD problem when you are trying to find out a dedicated quality metric for enhancement of mammograms. Then another thing is, as I have already told, that while you are selecting problems on mammograms, try to focus more on the mammograms with the dense background rather than just the mammograms which are fatty, because it is very easy to operate any filter on a fatty background. But the real challenge is to overcome the camouflaging of anomalies when you have these kind of dense images at the output. Another thing that which is again a challenge and which is to be considered when taking up the research problems. What the challenge is that I told you, when the boundary is very clear, right? You see that say that this is a benign tumor. When the boundary is having disturbances, it is having speculations, you say that this is a malignant tumor, right? But there is a third category also, where the boundary is not very circular and there are also not very clear speculations. Now, which category it should go? Can you call it cancerous or can you call it non-cancerous? But generally, most of our classifiers are binary and they are saying that either it is a benign one or it is a malignant. So certainly, I mean, it is not always necessary that if something is not benign, it is certainly malignant. So this is actually a third category images which coexist, which just require further investigation, further medical investigation, or maybe say a reanalysis on a different kind of a modality. So definitely such cases should be taken up with care when you are taking up classifiers or taking up feature extractors for these particular images. Then again, as I told you, the change in the shape, the change in morphology of these particular tumors is actually predicting the stage. So again, any filter which is focusing on the change of morphology of this filter could be called, a kind of a universal filter if it is able to predict, and or you can say it can give an idea, it can enhance or give proper response on all the different existing stages of a particular tumor. Again, not just visualization of tumor, but the same filter should be also able to visualize the calcification also. Because generally you see there are different filters which are focusing upon calcification detection. There are different filters, there are different algorithms which are working, focusing towards tumor detection. So it is a requirement that at least the filter should be one in one itself. It should be versatile in approach, that it should, take up different types of anomalies processing or validation under one particular head. Last but not the least, that the response with the human vision system is also equally important, because at times it happens, it doesn't mean that you're using a non-linear filter means that the response is always very good and in coherence with a human vision system. So it is also able to be understood that, HVS response is also important when you are designing such filters, because at times maybe for this particular image you may get a good value of some contrast index, but certainly this is showing a very poor response from a human vision point of view. So definitely you have to recheck into the fundamentals, that there are some problems, that why this non-linearity is being applicable to this kind of an image. Right now, these different filter combinations, as I have already told, that in the current work which I have discussed, this was generally a fusion of type 0 and type 2 filter. Over here, if you see the response, a more clear segmented response you can see. This is the response which is obtained with, say, the combination of type 0 and type 1 filter. This particular combination, this particular response is obtained. And this work, I mean, it is not that simple that, you are just picking up type 0, type 1 and combining. There are a lot of another consideration. There are a lot of another things which are taken into consideration, right? So this is another dimension of polynomial filters, right? Which is focusing towards edge enhancement of these mammograms. And this kind of analysis is already published in one work in the prestigious Computer Methods and Program in Biomedicine Journal of Elsevier, right? Another very recent work that I told you was the optimization thing. So this optimization of parameters has been also incorporated to some level with the genetic algorithm. And this work has been recently published in last year in September 2020 in IEEE Sensors Journal, where a contrast enhancement model was done using modified transformation based on multi-objective optimization. This work was done by one of my scholars for optimizing the nonlinear filter for mammograms. So I'll be thankful to all my collaborators who have been worked as a part of my research group in this particular research. And this is the team of doctors from my area who have been time to time, helping me with the diagnosis part, with the validation of results. So I'm really thankful and would like to acknowledge their support as well. So now I think you can open the session for questions.
Thank you. Dear participant, if you have any question, raise your hand or write in chat box. I will unmute you. Okay, no question. I would like to thank. Yeah. Okay, okay.
So somebody has typed in, I think, some question in the chat box.
Okay, ma'am.
Sir, I want to know about the. Hello, am I audible?
Yes, you are audible. Please tell me.
Okay. So, you were talking about the spatial resolution and image sharpness.
Yes.
So, sir, can you name some algos which can be used to sharpen the image, or while we are creating the histogram? Actually, I was working previously. I was working on images. So on MATLAB, I used to create a histogram of RGB image, a color image. So there I was facing these kind of challenges.
Let me clarify. You are Sneha, right?
Yes, sir.
Okay. See, there are two things. There is one more session of mine which has focused towards histograms, right? Now, what is the problem with histograms? Specifically, if you are applying histograms to normal images, it is fine. But if you are applying histograms to the medical images, again, there is a problem of over enhancement over there. And that is also not overcome in a very proper manner when you are using adaptive histogram equalization over there, or you are using CLAHE, that is contrast limited adaptive histogram equalization over there. So, I mean, as regards temporary work, clay could be a solution. But if you want to do some novel work, that means, you are supposed to say design or improve the performance of histogram equalization. Again, it's my advice that you go back and see that histogram equalization actually operates with the help of a transfer function, right? If you see that there is a sigmoidal transfer function at the back end, which operates as histogram equalization. So if you somehow go back and change the parameters of that transfer function, you will learn that histogram equalization can provide you better results, right? You can get better contrast improvement, and sometimes sharpening could be also there with your betterment of the transfer function of the image histogram, or you can say histogram equalization.
Okay, sir. Definitely, I will look into it. Thank you. Thank you so much, sir.
Okay. There was some more question. I think somebody has typed in. Anyone? Please come forward. I think it will be more interactive if you can directly put up the question and then we can discuss.
Sir, one participant is asking, any scope of fuzzy logic in medical image analysis?
Yes, of course, there is scope of fuzzy logic because, see, as I discussed right now, that tumors cannot be just, taken up in the manner that they are either benign or they are malignant. But there is a third category over there, which is a category which needs further investigation. Another thing which I told is that, say, from the proper benign tumor or say going up to a proper malignant tumor, there are a lot of intermittent stages which a tumor takes, right? Till it's transformed to a proper cancer or a malignant tumor. So if you really want to, refer or correlate with each stage of the tumor, then certainly you cannot work with a binary mode. You have to introduce the fuzzy logic concept over there. And it is already used. A lot of fuzzy filters are there, which are incorporated along with the processing of mammograms. Any more questions? think somebody has again.
Hello.
Yes.
Sir, very good afternoon, sir. We had a very
Afternoon.
good session. Thank you very much. I
My
have one
pleasure.
question, sir.
Uh,
Sir, I'm working on blood cells classification, sir, white blood cells
Okay.
classification
Okay.
in order to detect whether it is malignant or benign, sir. So there I had used clay contrast limited adaptive histogram equalization, sir.
So is clay is giving you, see,
Yes, sir,
when
but
you are working
since
on
I
the,
didn't had any ideal image to compare with, so I
that is
used,
the problem.
yes, sir, I
uh,
used Nike and MSC parametrics, sir, for
which
comparison.
parameter? Come again. Which parameter?
Nike, sir, Nike.
Okay.
It's a
I
MATLAB
advise
function.
you.
Yes, sir.
I advise you in this case that
Yes, sir.
don't go for any relative function, right? Where you
Okay.
require an ideal image. You go for some absolute functions over there. So
Blind.
there are a lot of no reference metrics.
Yes,
Like
sir.
there is
Yes.
one very common metrics by the name EME, that is
EM.
measure of enhancement, right?
Okay. Okay, sir.
EMEE, that is
Yes, sir.
measure of enhancement with entropy. So such absolute metrics can be utilized. So
Yes, sir.
that EME you can calculate for your original image. EME you can calculate for your transformed image. And if there is an increment in the value, you can make out that the enhancement is there. But I advise you that, this WC blood cell images are
Yes, sir.
actually not in that manner as if that of a proper medical image, and there the targeted task with these images is actually segmentation and counting of these cells. Am I
Yes,
right?
sir. Yes,
This
sir.
is what is actually required. So there, the focus is not very much on enhancement. The focus is to do segmentation and count the cells. That
Yes,
is
sir.
more important over there. So you cannot treat them at par with what we have discussed as in the case of these breast cancer images.
Yes, sir.
Okay.
But when we classify them as either
Huh.
cancerous cell or non-cancerous cell,
Yes, yes.
then I think there we have
Yeah,
to do
definitely.
pre-processing. So
There
we have,
though you have to do.
yeah,
Yes,
we have to
yes.
go for enhancement or we have to go for increasing its shape or some processing has to be done so that
Exactly.
to improve the
Exactly.
classification accuracy.
See, there, I think for those cells, I suggest you that morphological filters are more better because some way you have to adjust the change in shape or change in morphology of those cells, right?
Yes, sir.
So there, morphological filters can give you a better solution when processing those blood cells.
Yes, sir. But we need to compare and we need to tell us that this pre-processing step has improved the quality of the image.
So
So,
again, any quality metric can be used, and with that you can compare that which one is giving you an output. But
yes, sir.
again, this could be a preliminary result.
Yes,
So
sir.
later on, say when you are doing segmentation, counting, and classification, then at the final stage you can get to know that which filter has given you a better accuracy.
Yes, sir.
I
Yes, sir.
mean, you just can't rely on the temporary value of your quality metric, right?
Yes,
You
sir.
have to
Yes,
go
sir.
till the end solution, find out the accuracy. So maybe now that you have done pre-processing with 5 different filters. So you compare the accuracy obtained with all those 5 types of filters, and then you will be probably getting a clear idea that which pre-processing technique has given you better accuracy.
Yes, sir. Yes, sir. Thank you very much, sir. Yes, sir. I'll try, sir.
Yeah.
Thank you, sir.
Another, there was one more question in the chat box. Uh, Please come up. I think somebody was questioning regarding the fuzzy logic part. Okay, any more questions?
Okay, sir, no question. I
Okay,
would like to thank Dr. Vikrant Bhateja, sir, for delivering and enlightening us with their knowledge. Session was full of knowledge and interesting fact, especially the part covered computer-aided analysis of mammogram, limitation of mammography acquisition, type of mammograph, linear, non-linear filter, mathematical modeling of non-linear, for the betterment of mammograph image enhancement. I am pretty sure that precious knowledge that Dr. Vikrant Bhateja sir gave us will definitely help in our research in future. Thank you very much, sir.
Oh, okay, I have just shared one link. It is a Elsevier journal measurement where there is one call for papers regarding machine vision in the medical images.